Hello everyone and welcome back to the Analytical Element podcast. Today we are diving deep into the heartbeat of heavy industry with our episode title From Reservoir to Refinery, which analytical method work best.
Exactly. Crude oil isn't just black sludge, it is a highly complex mixture of thousands of hydrocarbons, sulfur, nitrogen, and heavy metals. To safely refine it into petrol, diesel, or jet fuel, we need absolute precision. So today, we are focusing on the real world scenario right here in Malaysia, monitoring feedstocks at a local refinery to prevent catalyst poisoning and meet environmental standards.
To help us break down the chemistry behind the barrel, we have a fantastic panel with us today. Pang Zuyan, Senior Refinery Engineer, alongside Nick No Hazira, our Analytical Chemistry Expert. Welcome guys.
Thanks for having us. In the refinery, knowing exactly what's in your crude oil stream means the difference between a multi-million dollar profit or a catastrophic equipment failure.
So before we can even run an analysis, we can't just pour raw crude oil straight into a dedicated instrument, can we?
Absolutely no. Raw crude oil is full of particulate matter, water, and heavy sediment that will instantly clog an analytical system. Sample preparation is the crucial first step.
Yeah, exactly right. It's depending on the target analytic. Let me say like sulfur content or validated hydrocarbon. Typically, we use this technique like solvent dilution using toluene or hexane to reduce the viscosity, or vacuum distillation to separate lighter fraction from heavy residue. For trace method analysis, we might even use acid digestion to break down the organic matrix completely.
So clean sample preparation ensure that the data we get downstream is actually reliable. Let's move to the core methods.
Today, we are evaluating two major pathways, which is modern instrumental analysis, specifically gas chromatography coupled with flame ionization detector, versus the classical wet chemistry techniques such as potentiometric titration for acid number tracking.
Let's start with the powerhouse, like gas chromatography. The basic principle relies on separating volatile component between a mobile phase, such as an inert carrier gas like helium, and a stationary piece inside a long, coiled capillary column. As the vaporized sample travels through the column, heat in oven. Components separate based on their boiling points and affinity for the stationary phase.
And as they exit the column, the FID burns the hydrocarbons in a hydrogen air flame, creating ions. The current produced is proportional to the number of carbon atoms, giving us a very beautiful peak on our chromatogram.
Fascinating. Now what about the classical wet chemistry side? Is titration completely absolute?
Not at all. For measuring things like total acid number or TAN or sulfur species like mercaptans, we use potentiometric titration. The principle here is a classic cytometration where the titration of known concentration is added to the oil sample dissolved in a solvent, and we monitor the change in electromotive force or potentials using an electrode to find the exact equivalence point.
So what is the difference between gas chromatography and wet chemistry?
Then we see at sensitivity like for gas chromatography is excellent while wet chemistry is just moderate, and for speed gas chemistry is very high and wet chemistry is a bit slower.
In the meantime, the operational cost for gas chromatography is high, while for wet chemistry is relatively low. For gas chromatography, the real-time utility is great for online loops, while wet chemistry is only for batch testing only.
So looking at this comparison, why would a refinery choose one over the other?
In a modern refinery, time is money. GC works best because it allows for automation and online tracking. We can inject a sample and get a full hydrocarbon fingerprint down to parts per million, also known as ppm detection limits. This is vital because even trace level of sulfur can ruin millions of dollars worth of refining catalysts.
Yeah, however, we mustn't not discount wet chemistry. The potentiometric titration require far lower capacity investment. If an offshore platform or a small local lab needs to quickly verify the acidity of a crude batch without deploying a $250,000 GC instrument, titration is equilibrium, robust, and reliable.
So while GC offers unmatched depth and sensitivity for complex compositional mapping, wet chemistry serves as a reliable, cost-effective gatekeeper for specific target bulk properties.
Let's look at the numbers. To prove how this method works mathematically, our team has prepared a standard qualitative analysis for calculating the total acid number of crude oil sample via titration.
Okay, let us assume we titrate a 10-gram sample of crude oil dissolved in toluene isopropyl solvent. Mixture against 0.1 potassium hydroxide titrate, and the value of KOS used to reach the potential matching endpoint was 1.5 ml, and the blend titration required is 0.1. And this is the formula you can use.
Where Vs is the sample volume 1.5 ml, Vb is the blend volume 0.1 ml, M is the molarity of KOH 0.1 mole per liter, 56.1 is the molecular weight of KOH in gram per mole. We'll be converting to mg, and W is our sample weight, which is 10 gram. So in the end, we found out that the total acid value is 0.7854 mg KOH per gram.
In the petroleum industry, the total acid number value above 0.5 indicates a highly corrosive crude oil, alerting the refinery that they must use specialized corrosion-resistant metallurgy or blend this crude down.
That calculation perfectly illustrates how raw analytical chemistry data directly detected operational decision in engineering.
So, to answer our ultimate question, which analytical method works the best?
The verdict is contextual. For comprehensive composition, refinery stream optimization, and ultra-low detection limits, gas chromatography is unequivocally the winner. But for rapid, low-cost, and also targeted verification of specific operational properties like acidity, classical wet chemistry still holds its ground beautifully.
An incredible breakdown from our team. Thank you all for watching. Don't forget to check our calculation appendix and reference sheet attached in the description below.
See you next time on the Analytical Element.